Hello friends, very good morning. Welcome back to my channel Siddhanath Nishandar. Hopes you are enjoying this channel. In the lockdown period, we're going to cover the different three chapters of the second part of the thermodynamics. Hopes you are enjoying and learn this all the three chapters. Okay, the our mechanical department going to arrange the series webinar series around the 40 hours in this month for the different domains. I am going to take the thermal domain. And these all are the webinars are value added beyond the syllabus. Okay. My today's first webinar, I'm going to cover some basic fundamentals, which is very important in the competitive exams and the gate point of view. So our aim is to cover some project-based learning regarding thermals, plus what is the importance of ISHRE, how to write a proposal for the ISHRE, that is the Indian Society of Heating and Refrigeration Air Conditioning. In coming webinars, I will going to cover. Okay, today's first webinar, I'm going to cover today webinar. I'm going to cover the fundamentals of thermodynamics and the laws. Okay, and then second webinar, I'm going to cover the applications. What we fundamentally studied, the basic formulas and how to apply in day-to-day life or the some social problems regarding. I told that suppose there is one room and there is one bulb is there about 100-watt bulb is there. Okay, the initial temperature of room is that, and after 24 hours what is the temperature of that room. Such questions we studied some different isobaric process in the classroom, but different number of students doesn't know the how to apply this isobaric process in that in day-to-day life or the engineering problem to solve such problems. If we focus on the gate exams, we study some gate questions papers. There are some basic questions are regarding the fundamental questions in day-to-day life or engineering questions where students fail to apply. Okay, so our purpose is to how to apply this fundamental. Okay, I take an example. Suppose there is the room. Okay, there is a constant addition process. The heat addition takes place of constant pressure. So the isobaric process, so MCP delta T is there. Okay, so you have to know how to apply the fundamental formulas, how to correlate. Okay, I'm going to take in next lectures, going to cover such a interesting questions in front of you. I'm going to solve. Okay, so is eight to nine webinars are quite interesting. Hopes you enjoying these coming webinars and this webinar also. And today's webinar is going to cover the fundamentals. I'm just going to revise. Is very important. Okay, so let's start with this PowerPoint presentation for this webinar. Okay. Okay, I'm starting the slideshow. Okay, that is the introduction to thermodynamics. Let's start with the introduction of thermodynamics. Okay, see here the different forms of energies. If you see here, okay, I'm choose the pointer here. If you see there is a one form of energy, the nuclear energy is there. Okay, the light energy is there. That light energy is we see is connected with the battery. That is the chemical energy is converted into the light energy and the heat energy. There is a magnetic energy, different forms of energy there. If you see here, there is also showing the one tree and the fruit on the tree in the form of potential energy. When dropped down, the converting that potential is coming to kinetic energy. I taken simple examples in day-to-day life of different forms of energies happen is around us, and we know the law of conservation of energies. The energy can't be created, not be destroyed. Okay, it only changes forms, one form to another form. If we see here, the solar energy, it's converted to the chemical energy. Okay, and then it's converted into, if we use for that heating purpose, that energy is converted into the heat energy. So there's different forms of energy. We know that. I just going to revise. Okay, take one example of car. If we see here, if we supplying the oxygen and the fuel, okay, as a chemical energy, we see here CXHY as a fuel and oxygen. That is the chemical energy supplying to the car. and that chemical energy is converted into the heating energy. That heat energy is again utilized to reciprocate the piston, and finally we get the mechanical energy. So simply, the combustion of fuel converts chemical energy into a mechanical energy. If you see in this example, and to propel the vehicle to overcome the friction, so it is the law of conservation of energies. And if you see, there is the exhaust. Okay, so developed energy utilized to propel the vehicle. Some of the energy is lost during the radiation. Some of the energy is carried by the heat carried by the radiator. So the energy is balanced. Energy is only transform. It is the law of conservation of energy. It is the first law, or is the statement of the first law of thermodynamics. Okay, let's start with the now different thermodynamic systems and the first law of thermodynamics. If you see here, there is one chart I'm showing. There is a thermodynamic system, and we know that generally I told that the thermodynamic system classified in three groups: closed system, isolated system, and the open system. Okay, just you will remember these three systems. Okay, there are other another systems there also, but just we focus now on the three systems, the mainly the closed system, isolated system, and the open system. Okay, and that two systems actually classified in two groups. If you see here, control mass system and control volume system. Okay, in control mass they are classified closed and isolated, and control volume they are classified open system. They are two very important as a gate point of view, and some objective questions, the multiple choice questions, they ask them, or for into point of view, which system under control mass system and the which system under control volume system. Why it is called as a control mass and why it is called as a control volume. Okay, if you understood, focus here. In closed system, you know that if you see in the closed system, there is only transformation of energy takes place, but there is no transformation of energy. Okay, in closed system, there is no transformation of mass, I repeat, but there is only transformation of energies. The energies may be Q or energy may be W. Okay, the energy in the form of heat or the energy in the form of W. That is the closed system. In case of open system, there is a transformation of mass as well as energy across the boundary of the system. This is very important. Across the boundary of the system. The word is very important. In case of isolated system, there is no transformation of energy as well as mass. Okay, if we focus closed system, okay, this phenomena is we around with mass only. And control volume, suppose in control volume I am taking an example of turbine. Okay, the purpose of the turbine is to focus to mechanical energy. Okay, what happen in what on which principle it works? We particularly design one system. Okay, we know that the definition of the system, a particular area or space where some thermodynamic activity going to happen. Okay, in turbine what happen? We design such a volume. We know that the construction working of the turbine, there is one shaft. On this shaft there is one rotary disc. On the rotary disc the number of blades as provided on its periphery. Okay, this is a designed system. It's a closed volume system, sorry, control volume system. Then and then when steam flows over that designed system, okay, when the steam is flows over that designed system, then and then that steam energy is converted into mechanical energy. If steam suddenly flows over the atmospheric phase, doesn't happen any work. So particularly that steam is going to pass some particular design, some particular volume. So it is called the control volume. So the word control volume is very important in this case. So open system is the mainly called as a control volume. All open system you design such a way that when mass flows through that system only, it gives some energies. It may be heat, it may be work. Again, I explain in the coming. We will take a particular examples. and you can understood. Already we go through that, but now it is the I'm going to deep cover here. Okay, let's now it starts with the some I preparing some notes. Okay. If you see, the word thermodynamics is derived from the Greek word therm and dynamics. It is a combination of therm and dynamics. The therm stands for heat, and the dynamics is known. You know that the dynamics is the motion. So heat power, heat motion is the fundamental. And if you see the lots of applications. Okay, if you see the compressor in last in my previous videos, we see that compressor in detail, turbine in detail. Okay, coming webinars, I'm going to cover some part of the refrigerators. Okay, we also see the rocket engine, jet engine in detail. Okay, in solar collector, okay, the solar collector and refrigerator, I'm going to cover through some projects, the industry based projects. Okay, I'm going to cover where the refrigerator and the solar collectors. The remaining parts will apply in the second part of the thermodynamics. Okay, where defined system is the defined area of space where some thermodynamic activity is going to take place. Okay, with defining different systems, we study different systems like a compressor. If you see the compressor, turbine, jet propulsion, rocket engine, at a particular volume they are designed. Okay, if you see the example of the gas turbine, okay, or the turboprop engine, if you see here, they form control volume. Initially, some air is sucked to that drag section. Okay, that ramming effect, there is some partial air is compressed, and again it is supplied to the combustion chamber. Okay, and after that, that fuel is added and that combustion product flows over the turbine. After exhaust through that nozzle is released to the atmosphere. Okay, where is the system is open when the air flows over the inside the turbine, and then we get some output, then and then get some jet propulsive motion, some reaction force. So we focus, there is a way when we call the open system, this system is called as a control volume only. Okay, the thermodynamic system I cover. We know the surrounding, everything outside the system is the surrounding. Boundary means the system and the surrounding is separated by the thermodynamic boundary, or is also called as a system boundary. When the system and surrounding put together to form this universe. Okay, now we see the closed system. You know that there is only across the boundary there is only transfer of energy, but mass remains constant. That is the closed system. Okay, now we see the one example of the closed system, that is the pressure cooker. Okay, and if we see the fundamental example of the piston cylinder arrangement. Okay, when you supply heat, what happens? The gas energies, okay, the gas inside the cylinder, okay, the gas included in cylinder, what happened? Because of absorbing heat, the gas starts to expand. Okay, so the piston moves in upward direction. So piston moves in upward direction. Okay, if you see here, I provided one stopper. The that piston moves in upward direction, that gets energy as a work. That is the reciprocating motion. When you're supplying energy as a heat, Q energy, Q, and we get W. So there is a transformation of energy. One form of energy enter, and one form of energy crosses the boundary of the system. So what happened? I told that the whole system, whole universe is worked on principle, the law of conservation of energy. So initially I cover, that is the law of conservation of energy, where some energy in means the Q energy is in. Okay, and you know that the energy can't be destroyed. So that energy is converted into work energy. Okay, and also we know that the heat and work are mutually convertible into each other. This is the another statement of the first law of thermodynamics. So we follow the first law of thermodynamics, we follow the law of conservation of energy is there. So Q is converted to W, but mass of the gas inside the system remains constant. In case of pressure cooker, one form of energy is enter. Okay, the inside surface of the pressure cooker and is covered from the boundary. The no mass of the food can cross the boundary. Heat can leave the boundary during the whistling process. Hmm. If you see one form of energy, that is heat energy supplied, that heat energy transport to the inside the food, inside the water is there. Okay, and after that particular pressure or heat developed inside the chamber, the excess steam energy is released during the whistling process. There's only transformation of heat energy and the releasing the steam energy, but mass of the food inside the chamber is remains constant. There are some examples of the closed system. Hopes you understood now. Okay, then now applications. This is the refrigeration system. It's very important in the day-to-day life. We see the freeze. Okay, that is the refrigerator system. It works on principle of VCRS, vapor compression refrigeration system. Okay, where we study, we know there is a compressor. If you see in the freeze, okay, possible I'll show VCRS. Here I'm showing searching a 3D view. You can understood. In the VCRS system, if you see, okay, yes. Okay, the system, you know that there are the four main components. We know that the compressor is there, condenser is there, expansion valve, and the evaporating coil is there. Okay, if you see this image, okay, copying this image so we can easily understood this system how it actually works. Okay, see there. If you see there is a compressor there at the back end of that fridge. Okay, if you observe, and there is a condenser coil. Okay, there is a capillary tube, and if we see in the fridge, there is a first apartment compartment. Okay, there is the evaporative coils. Okay, this is the application, the best application of the closed system. Okay, this is system. There is a working medium is the refrigerant. Okay, the refrigerant is the we know the refrigerant working medium. It works where with having the latent heat, having some basic particular properties. So it is used as a refrigerant. We call it as a refrigerant. Is as a working medium. It can't flow across the boundary of the system. Okay, if you see in the refrigerant system, the compressor, if you see here, is showing the highlighter. The compressor suck the low pressure, low temperature vapor refrigerant. Okay, the refrigerant is a working fluid. Okay, that compressor, that low pressure, low temperature vapor refrigerant suck from the evaporating coil. Okay, and pass to the condenser. Now, role of compressor, we know that it increases the pressure. it increases the temperature. Okay, that now high pressure, high temperature compressor flowing over the condenser. Okay, now if you observe at the back end of the freeze, we generally told that if we keep the freeze around half centimeter or the around the 15 to 20 centimeters, we keep from the away from the wall. So what it indicates, there is we provide some circulation of air over that coils, that is the air cooled condenser, which rejects heat to the atmosphere. Okay, what happened now? That low pressure, low temperature gas becomes high pressure, high temperature compressor and condenser after rejecting the heat to the surrounding. That now gas becomes now in liquid form. Okay, it but be in higher temperature. So now the pressure is remains constant and the temperature is going to drop in a temperature, but pressure remains constant in the condenser coil. But the form is a liquid now, but temperature reducing. Suppose there is a 80 degrees Celsius temperature is around going to 40 or 35 degrees Celsius temperature is there. Okay, this main role is now the capillary tube here. In capillary tube, there's sudden drop in an area. Okay, in capillary tube, you will see the different flows over in coil, and when it flows to the capillary tube, there's sudden drop in an area. So if we see the small cross-sectional area here, and this is the large cross-sectional area, when fluid flows over that higher cross-sectional area to the lower cross-sectional area, the sudden drop in a pressure and temperature, so that liquid represent temperature becomes very, very low, and so cold temperature. So also the evaporative is also called the chiller, and the very low temperature represent flows over that evaporative coils. Okay, and we know that heat always flows from higher boil to the lower boil temperature. Where what amount of food contained in the chamber. Okay, there is a high temperature, and that heat absorbed naturally by that evaporating coils or the cold refrigerant flowing over that evaporating coils, and so the heat absorbed by that refrigerant inside the tube only, and so that cold refrigerant absorbing heat, it becomes vapor, and that again vapor is absorbed by the compressor, and this cycle is going to continue. If you see here, the compressor, condenser, capillary tube, and the condenser together form a system. The main four systems are there. Okay, now I told that the condenser releases heat to the surrounding. If we feel there is a temperature in the kitchen, this maybe we feel is higher as compared to the another rooms. Okay, why? Because the condenser continuously rejecting heat to the surrounding. Okay, and the refrigerant or working fluid always flows over the inside the tube only. Okay, so the mass of the refrigerant remains constant, but is exchanging energy. How it exchanging energy is very important here. The exchanging energy is because of its phasing change phase. Okay, so the refrigerant is a phase change material. Suppose in condenser, the phase change becomes vapor to liquid. Okay, in case of evaporator, the phase changes from liquid to vapor. So the refrigerant has a property, this is a phase change material, and because of that phase change property, we are exchanging energies. So there is mass remains constant. So the refrigerant is the best example of the best application of the closed system. That is the refrigerant system. We see here the no mass of the working substance can leave the system. The energized electric work enter. To run the compressor, we know the refrigerator is not automatically started, it consumes some electricity. That is the electric work. The energy electric work enter inside the chamber. Okay, and that electric work is converted into some energies lose. Energized heat is rejected by the condenser, and energized heat absorbed by the evaporator. So one energy in. Okay, the interaction of energy takes place here, and the interaction of energies in the form of heat, it is crosses the boundary of the system. So again, follow law of conservation of energies. So electric work is converted into heat energy, and we get the output at the evaporator. That is the cooling effect. That is the transformation of energy. It's very quite interesting. We follow only universal laws only is there. If we see bulb and lamp, energy as the electric energy enter inside the system. Okay, there is no transformation of that filament or the inert gas in that inside the chamber. Okay, there is only transfer of heat and light energy. Okay, so the mass of the system remains constant. Now, open system is also we call as a control volume is very important. The mass as well as the energy transfer across the boundary of the system. Okay, if we flow through the nozzle, flow through the pipe. Okay, if we so the take example of simpler nozzle here. Okay, initially some energy is there, some potential energy is there before entering in this chamber, and at the outlet of this chamber, if we convert is that pressure is converted to the kinetic energy. So the transformation of energies takes place here. Initially, the potential energy is there, okay, and the kinetic energy is there. So potential energy is converted into kinetic energy. So there and also there's a mass in and mass out. That is the we follow. There is the law of conservation of mass is there. Okay, mass at inlet is equal to mass at outlet. So mass in, mass out, energy in, energy out. The potential energy maybe that converted to the kinetic energy. These are the example of open system. There's another application we know the compressor we studied in detail. Okay, what amount of energy enter in the compressor? Now tell me the electric energy. The electric energy in, and that electric energy is converted into that rotary motion is converted to reciprocating motion. The resultant that fresh air inside the chamber. If you see the fresh air come inside the chamber, okay, and the if you see the fresh air inside chamber, and the output is the high pressure, high temperature is the output of the. This is the output of this system. Okay, now see which form of energy is in and which form of energy is out. The electric energy is in, okay, and the resultant that which form of energy is out, high pressure high temperature energy is out. What about mass? Low pressure mass in and the low pressure mass, so high pressure mass is out. So mass in, mass out, and the electric work is electric energy is converted into heat energy. So there is a transformation of mass as well as transformation of energy. The different examples now in open case of, you know, the you see the example of IC engine is the best application of open system. If you see the mass of fuel and air come inside the chamber, result in that mass in and the mass out in the form of combustible products. So mass in, mass out, and result in that we get energy as work. So we propel the vehicle, we get rotary motion, power available at the crankshaft. If you see, and at the same time, you some heat is the releases to the atmosphere. In case of two-wheeler, if you see, there is the radiator, there is a baffle plates on the two-wheeler. In case of four-wheeler or the high cc engine, there is the radiator. So some amount of energy is releases through that radiator or the baffle plate, and the some amount of energy utilized for work. So the IC engine, turbine, flow through pipe, flow through nozzle are the best example of the open system. There's a water heating system is there. Is also open system, water in, cold water in, hot water out. Suppose there is the electric heating coil in there, the electric energy is converted into heat energy. So one form of energy enter as the energy as electricity is enter, electric energy, and the energy as the heat energy. That is the, if we see the energy as the heat energy. So the electric energy is converted into heat energy. Okay, we see the in last semester in detail also. Now this is very important term for the next webinar series. So I'm going to cover detail here again. You know the turbine. Okay, now we see the few example of isolated system here. In isolated system, there is no transfer of mass and the work takes place. Okay, the mass, no transfer of mass and the work takes place across the boundary of the system. So this is the isolated system. If we take example of thermos flask is also. Okay, there is a now difference in the closed system and the open system. Is also called closed system, also non-flow system. Okay, and this is called a flow system. Okay, in open system, the working fluid flows over the control volume of the chamber. Okay, in non-flow system, it doesn't take meaning that the mass is in constant. Why it's called non-flow system? The mass flows inside the boundary of the system only. So it is called as a non-flow system. An open system, flow system, that mass of the fluid crosses the boundary. So it is called the flow system, which crosses the boundary, mass crosses the boundary in and out during crossing the boundary of the system. But in case of non-flow system, it doesn't crosses. Okay, the different certain quantity of matter is considered for study. You are called, why it's called the control mass? The reason is that the certain quantity of matter is considered for study, and where the certain region is considered for study is very important. The certain region is considered for study, and the certain quantity of matter is considered for study is very important word. Okay, if we see the example of the VCRS system or the pressure cooker, the system is designed for particular mass. Okay, so for certain quantity of food, okay, is the occupying the that pressure cooker. Okay, certain amount of the filament is included in the bulb. In case of VCR, the certain quantity of mass of the refrigerant gives the output. So what amount of matter flows inside the system, it decide the output. Okay, is very important. But in case of open system, if you see, okay, what region we designed, for example, gas turbine, water heating system, or the nozzle, so what amount of region we decide, it considers the output of the system. So it is the region is very important. Okay, and here is the matter is very important. They are the systems are very important. Okay, in hopes you understand the whole the systems, how it is classified: open system, closed system, isolated system. Okay, just in short revise now. The state, we know the exact condition of system at a particular instant, we call as a state. Initially state 1, at the end of compression, if the state of the system is that is a high pressure, high temperature of the, suppose the gas is there, that particular state is that high pressure, high temperature. When it releases, when it expand at point 2, there's a drop in a pressure and drop in 2. So state varies according to condition. So the definition of state is very important. Exact condition of a system at a particular instant is very important. Hope is the particular instant is word is very important for case of a state, because at instant to instant it varies, or any defining any state we need minimum two properties, the two thermodynamic properties. To define state, at least two thermodynamic properties are necessary. Okay, now in path function and the point function is very important. The path function, there is a, if you see, there are certain quantities which can't be located on a graph. If you see PVT's graph, we locate the pressure on the graph, temperature on the graph, volume on the graph. Okay, the specific enthalpy, entropy, we also plot on a particular point what is the exact condition. But some phenomena, some properties which can't locate it on a graph, which is the phenomena of the output of the whole process. For example, if you take a same example of the piston cylinder here, okay, we supplying heat energy. Okay, what happened? The piston starts to expand from the top dead center to the bottom dead center. The whole output is that from point 1 to from point 2, the piston moves TDC to BDC, a result out of the supplying heat. Okay, so it is very difficult to locate a single point as a heat on a graph. The output is the weight volume is going to change. If you see on PV diagram, the point 1 to 2 is the there is change in volume. That whole volume is changed because of supplying heat. So we can't locate as a point as a single. So such a phenomena, there's such a properties we call as a path function. It's very important. The path function of heat and work. We always remember these two words: path function, heat and work. Okay, friends. Hope you understood today's webinar. Okay, coming webinars, I'm going to cover the remaining part. Okay, hopes you enjoying the today's lecture. We cover the open system, closed system, isolated system in details. Please go through this webinar, repeat, and coming lectures, I'm going to cover now the very important part, the first line, the second law of the thermodynamics. Hopes you are enjoying this today's session. Thank you.